The second demonstration that I want to do for you involves, I'm just going to set this aside. Thank you. Illustrates another very important principle, and that is that calcium carbonate, which is the basic building block of all of these calcifiers, oysters, clams, mussels, oysters, those are all made of the same stuff as chalk. Now, chalk, in the olden days, when I was growing up, most chalk that we would use in school was pretty pure calcium carbonate. Today, other substances have been added to it to make it less dusty, less breakable, etc. So if you want to try this at home, you need to get almost pure chalk, which is what this is. And what I'm going to do is to show you what happens to chalk or other types of calcium carbonate when it is in regular water, when it is in water, half vinegar solution, which is more acidic. As you know, vinegar is a weak acid, so I've combined water and vinegar there. And in this container, this is all vinegar. And so we have an increase in the amount of acidity from normal water, half vinegar, and pure vinegar. And what I want you to notice is that when we put calcium carbonate chalk into the water, and the same would happen if you put it into seawater, nothing happens. This is the way the ocean has been for a long time. Shells are fine in water, they don't dissolve. If you put chalk into half water, half vinegar, you can see some bubbling start to happen. That is the calcium carbonate that is beginning to dissolve in the weak acid and releasing carbon dioxide, bubbles of carbon dioxide. And if we put the chalk into pure vinegar, you can see that it starts bubbling much more quickly, much more rapidly, and is in fact dissolving much more rapidly. So here we have just a couple simple demonstrations that illustrate some very basic principles of what happens in oceans as they absorb the carbon dioxide that we have put into the atmosphere. I want to be crystal clear here. The ocean will never be as acidic as vinegar is. I have used it here simply as a visual demonstration of what happens when you increase the level of acidity in a solution, what happens to calcium carbonate shells. To show you what actually happens in seawater, the seawater that is projected to be affected by increased CO2 by the end of this century, I have a video clip, and I want to tell you a little bit about what it shows and then start the clip. The first 10 seconds will show you a living, swimming pteropod, one of these small animals that I spoke of earlier. It's a beautiful creature about the size of a lentil bean. It's incredibly important as a food source for juvenile salmon, for mackerel, for pollock, for herring. They are very, very abundant in oceans throughout the world. After that, you will see what happens to a pteropod in seawater that is the same chemically as seawater that is projected by the end of the century. So let's start the video clip if we could, please. And you will see first, once we get to it, impacts of ocean acidification. This is a swimming pteropod, a sea butterfly, swimming through the ocean. It's a small shelled mollusk. This is the way it looks naturally. This is a pteropod shell that you'll see time-lapse photos of what happens to the shell in seawater after 45 days, projected for the year 2100. And finally, this last clip is an animation illustrating from the year 1765 to 2100, the effect of increasing ocean acidity on the availability of the calcium carbonate mineral that pteropods, corals, and other organisms need to create their shells and skeletons. This is under a business as usual emissions scenario, and the change in color from purple to blue to yellow to red indicates increasing ocean acidity and decreasing availability of the calcium carbonate that is needed for shells and skeletons. Ocean acidity has increased by 30% since the beginning of the Industrial Revolution, just over 200 years ago. This increase is 100 times faster than any change in acidity experienced by marine organisms for at least 20 million years. By the middle of the century, it's expected that coral calcification rates will decline by a third, and at that point, erosion of corals will outpace new growth, making many coral reefs unsustainable. And by the year 2100, vast areas of the ocean, ultimately shown here in red, will have reached levels of acidification where pteropods, corals, and other important marine species will likely be severely compromised. So in conclusion, our understanding of the impacts of ocean acidification is relatively new. Roughly 2/3 of the published research has come to light since 2004, which is why you probably haven't heard a lot about this issue. Thanks to Congress's action in passing the Federal Ocean Acidification Research and Monitoring Act, more attention will be given to this subject, particularly by scientists at NOAA and our partners at the National Science Foundation and in academia. Nonetheless, our fundamental scientific understanding of the basic chemistry of ocean acidification is sound. More CO2 emitted into the atmosphere will increasingly lead to more CO2 being absorbed by oceans. That will make oceans more acidic. And we are now beginning to understand the ocean's very capacity to absorb CO2 from the atmosphere is being degraded by ocean acidification. These mechanisms can only be addressed by decreasing the amount of CO2 that enters the atmosphere. The dramatic impacts that ocean acidification can and will have on marine ecosystems are clear. Thank you, Mr. Chairman.